Hi viewers, welcome to my channel. This is Anthony Vijay. In this video, we will be going to see about graph traversals. So first of all, we will be going to see about the introduction part of graph traversal. So graph traversal is mainly used for searching a vertex in the graph, and it is used to decide which order to follow for searching a particular vertex, and it also used to find the edges in the searching process without creating a loops. And it means graph traversal will visit all the vertices without creating a loop. When I talk about graph traversal, there are two different types. One is DFS, that is depth first search, and the second one is BFS, breadth first search. So first of all, we will be going to see about depth first search. So depth first search will be going to produce the final outcome is spanning tree, and which will not follow any of the loops, and it follows a stack data structure. The size of the stack data structure will be depends upon the number of vertices available in the particular tree. Let's have a look about the following steps to be involved in implementation part of DFS traversal. The first step, we are going to define the size of the particular stack. So that depends upon the number of vertices available in the graph. Then we can choose any vertex as the starting vertex, and then we are going to find the adjacent vertices of particular starting vertex. And if you are visiting the particular adjacent vertices, after that we are going to push it into the stack. So every time we are going to find the non-visited adjacent vertices. After that we are pushing that particular vertex into the stack. So this particular process will be repeated for n number of times. At one point of time we are not able to find the non-visited particular vertex, and that time we are going to apply a backtracking technique. So this technique will be used to backtrack from the previous node, so that we will be pop up the topmost element from the stack, and this particular process will be continued till the particular stack is empty. Finally we are removing the unused edges. After that we will find the spanning tree. So let's see the implementation part with the help of diagram. So in this diagram we have 7 vertices A, B, C, D, E, F, G, H. So I start with the vertex A. So here A is a starting vertex. We can choose any vertex as a starting vertex, but here I am taking A as a starting vertex. So once we are visited A, we are pushing into the stack. After that we have to find the adjacent vertices of A. So there are 3 different adjacent vertices. One is B and E and D. So these 3 vertices are connected with A. If any particular vertex is connected with A, so that is adjacent for A. So we can choose any one from these 3, B, E, D, but I have chosen B here. So after that I am visiting B. So once I visited B, I am pushing that B into the stack. After that I am going to find the adjacent vertices for B. So again for B we are having vertex E as well as C. There are 2 different vertices are there, but I am choosing C here. Once we are visited C, we are pushing that C into the stack. After that again we are going to find the adjacent vertices. So here for C we have E and F as well as G. Totally we have 3 vertices, but I am choosing E here. So after visiting E, we are pushing into the stack. So every time visiting and then pushing into the stack. So this particular process to be repeated. So after that, once we are reaching E, now we are going to find the adjacent for E. So for E there are 2 different vertices are there. One is D as well as F, but I am choosing D. Okay, so after visiting D, I am pushing that D into the stack. Now after D there is no non-visited node, because D is for D, A is there, A is already visited. No other vertices are there for adjacent for D. So we have to apply backtracking for this. So backtracking means what? So we came from E to D. So we need to go back to E again. We have to go back to E again. So for that process, we have to remove the topmost element. So here the topmost element is what? D. So we need to remove the D from the stack. So when we are applying backtracking, so on that time we have to pop the element from the stack. So here D is removed. So that's why we are go back to E again. Okay. So because we are not visiting again, so that it is dropped out. Okay. After E, once again we started the adjacent process. Here after E we have adjacent as F. So after visiting F, we are pushing into the stack. Okay. After F we have G is non-visited, so that again we are G is visited and we are pushing into the stack G. So we have visited all the vertices now. So after G there is no other vertices to be visited. So now again we are going to apply the backtracking. The main thing is we are going to make empty the stack. Okay. So right now the stack is almost full, so we need to apply backtracking all over the graph. Okay. So now after G, no more adjacent vertices. Now we are going to apply backtracking. So backtracking means what? We have to go back. Okay. So already we came from F to G only. So we need to go back means G to F only we have to go. Okay. So in the next see here we are going from G to F. So G to F means what? We are so I told you already in the backtracking process, if you are applying backtracking, so the topmost element will be removed. So in the previous step we have a topmost element is G. Now in the next step G is removed. Right now we have F is a topmost element. So we all in the previous iterations we move only from E to F. Again we have to move from F to E. So this is the backtracking process. So that is applying here. So that again we have to remove the topmost element. So right now we have top is E. So after E we have to go to C. Okay. So this particular process will be repeated until the stack is empty. So E to C. So this is called backtracking. So again topmost E will be removed. Right now we have A, B, C. So after C we have to go back like this. Okay, C to B. So after applying this, C will be removed from the stack. Right now we have A and B. Right now the topmost is B, so we are going backtracking. So B to A. So in this backtracking the particular topmost element, that is B, is removed. Okay, so right now we have only one element is there. So after that there is no other vertices are there for A. We are applying backtracking for A. Okay, so we are removing that A also. Okay, so that almost all the process is over. Right now the stack is empty. Now we have to remove the unused edges. Remove the unused edges, so that A to D is not available and A to E is not available. These are the unused edges we have to remove, and B to E is not available, and C to F is not available, and C to G is not available. So while removing the unused edges, we are getting the spanning tree. So what is the use of spanning tree means? We have to connect all the vertices with minimum number of edges. That is called spanning tree. See here we have 7. We have 7 vertices. For out of that, how many edges we are having? 1, 2, 3, 4, 5, 6. So for 7 vertices we have only how many edges? 6 edges. So this is called spanning tree. So this is called depth first search. We are applying this with the help of stack data structure.
Please like and subscribe to my channel and press the bell icon for regular updates. Thank you very much for watching.